Welcome to Fast Math Solutions on Math with EJD. Today we have a very interesting question to show that 10 raised to the power n plus 3 times 4 raised to the power n plus 2. That dot is actually not decimal point, it's actually multiplication. So times 3 plus 3 times 4 raised to the power n plus 2 plus 5 is divisible by 9 for all natural numbers. Okay. So you should know that this question borders on mathematical induction. I should do a full video these days on one of these days on mathematical induction, taking you through the whole process. Okay. And generally speaking, anytime you have to do mathematical inductions, there are 4 basic steps. The first thing is whatever thing you're told to prove, you have to check if it is true for n equals 1. That means for this expression, for instance, put 1 for n, evaluate it and see if the result is divisible by 9. Then do the same for n equals 2. Then when you get to n equals k, just assume, because I mean there's no other way to establish that. So you assume for n equals k, and then you now establish for n equals k plus 1. Now, if you're wondering what that is, let's get into it and see what it looks like. So first thing I said, step 1 is to check for n equals 1. So the expression is 10 raised to the power n plus 3 times 4 raised to the power n plus 1 plus 5. So to check for n equals 1 means to put 1 for n. So you have 10 raised to the power 1 plus 3 into 4 raised to the power 1 plus 1 because n is now 1 plus 5. So that is 10 raised to the power 1 is 10. Then you have 3 here. This is 4 raised to the power 2 because 1 plus 1 is 2. Then you have 5. Then you have 10 plus 3 into 4 raised to the power 2, 16 plus 5. So 3 times 16 is 48. This is 10. This is 5. And then everything sums up to 63. And 63 is actually 9 times 7. So that means when you put n equals 1, the expression is divisible by 9, So the next thing is to go for step 2. Check the same thing for n equals 2. So now you have 10 raised to the power 2 plus 3 into 4 raised to the power 2 plus 1 plus 5. 10 raised to the power 2 is 100, of course, and you have 3 here. Then this is 4 raised to the power 3 plus 5, and you have 100, 3. 4 raised to the power 3 is 64. That's 4 times 4, 16 times 4, 64, then plus 5. Then all that will evaluate to this 100. 3 times 64 is 192, then 5. 100 plus 192 is 292 plus 5, that's 297. And then 9 goes there. So you have 9. 9 in 29 is 3. Remember that 2. 9 in 27 is another 3. So again, when you put n equals 2, you discover that the expression you get is divisible by 9. So the first two conditions are established. So for step 3, all you just have to do is to assume. So step 3, assume it is true for n equals k. That means that 10 raised to the power k, instead of n now, you put k. So 10 raised to the power k plus 3 times 4 raised to the power k plus 1 plus 5 is equal to 9z. This is the assumption now that this expression is equal to 9z, where z is an integer, okay? That is what it means for something to be divisible. That if you divide that expression by 9, you will get an integer. So that means if 9 goes here, you're going to get z, which is actually an integer. So you assume for n equals k. So 3 steps done. We have the conclusive stage where we actually do the final proof. So the last thing to do is to establish. Now, it's very important to take note of this assumption because it will be useful at the establishing stage when we do for n equals k plus 1. I actually left a space here because I was hoping that I might need to express this in a particular way that will fit into the expression I'll be doing next, but I later discovered it wasn't necessary. So sometimes it will be necessary to express this in a certain way so that you can actually put it into this last part. Okay. So step 4 is to establish for n equals k plus 1. So how do you do that? So wherever you had n, you had 10 raised to the power n plus 3 times 4 raised to the power n plus 1, 4 raised to the power n plus 1, all that plus 5. So now instead of n, you now have k plus 1. Instead of n plus 1, now you have k plus 1, which is standing for n and the plus 1 normally. So that's what's happening there. Okay, so plus 5, right? So the next thing is we have to now you need to make some moves to get to the result. So what is happening here is that 10 raised to the power k plus 1 is the same thing as 10 raised to the power k times 10 raised to the power 1 from the law of indices, right? 10 raised to the power k times 10 raised to power 1 is the same thing as 10 raised to power k plus 1. So we can break it down this way. So you have 3 here. Of course, like I told you, 3 is multiplying everything here. That's why I did it this way. But now k plus 1, so you can now say, 4 raised to power k plus 1, this is it here. And this other one, I separated it. And what I'm actually trying to drive at is that from this expression now for k plus 1, I want to get exactly, I want to get this expression out of this k plus 1. So if I'm able to get that, then I can slot in 9z for it, and then we see what happens. So my purpose here is to get that expression. So I know that this is multiplied by 10. The only way to free myself from that is to break this 10 into 9 plus 1. 10 is 9 plus 1, so I can easily get 10 raised to power k out of here. So this 10 raised to power k is freed. So I have 9 raised to power 9 into 10 raised to power k. That's 10 times 10 raised to power k times 9. That's 9 into 10 raised to power k. 10 raised to power k times 1. I have this. So we have 10 raised to power k waiting for what we can do with it later. So then coming here to 4 raised to power k plus 1, 4 raised to power 1. So this 4, so I broke it into 3 plus 1. So I can get this 4 raised to power k plus 1 out. So here I have 4 raised to power k plus 1 times 3. That's 3 times 4 raised to power k plus 1. 4 raised to power k plus 1 times 1. That is 4 raised to power k plus 1. So, and then you have the 5 out here. So again here, this is 9 times 10 raised to power k is 9 into 10 raised to power k. Then you have the 10 raised to power k standing here. And then 3 times 3, that's 9. That's 9.4 raised to power k plus 1. And like the dot is multiplication. Then 3 dots, you can see this is 3 times 4 raised to power k plus 1. So these 3 dots now is happening here. So we have been able to free 10 raised to power k plus 1. Now we have 3.4 raised to power k plus 1 plus 5. So it looks like everything is going well. But then you can see that the things we need to free are getting freed, like this, and this, they are free now. But look at this other one, this and this. They have 9 as a whole number in common, so you can factorize 9. So you have 9 into 10 raised to power k plus 4 raised to power k plus 1. So you factorize, because this is 9 times 10 raised to power k plus 9 times 4 raised to power k plus 1. So, and then you now have this 10 raised to power k plus 3 raised to power 3.4 raised to power k plus 1 plus 5. And then don't forget, from where you assume that the expression is true for n, this expression is 9z. So take it back. So this whole expression can now be 9z. So you have 9 into 10 raised to power k plus 1. 9 into 10 raised to power k plus 4 raised to power k plus 1 plus 9z. So 9 is common. So you have 9 into 10 raised to power k plus 4 raised to power k plus 1 plus z. Don't forget, this is an integer already. So for whatever value of x, if you put 1, this expression will be an integer. If you put 1 or any integer like that, any natural number, it is all going to be there. So this whole expression is going to be like an integer. So at the end of the day, you can actually say that 9 is like maybe 9j, where this j is an integer, where j represents this whole expression. So having established that, finally, you can now say, since 10 raised to power n plus 3.4 raised to power n plus 1 plus 5 is divisible by 9, for n equals 1, it was true. For n equals 2, then we assume for k, and then it works for k plus 1. Then you can say that it is true. Then it is true for all natural numbers. It is true for all natural numbers. And that's how to treat that question. See you in the next video. Thank you.